Welcome to today's lesson on the behavior of a magnetic compass and the evidence that the Earth's core is magnetic. We will begin today's lesson by learning about magnetic compasses and how they work. Next, we will explore the characteristics of the Earth's core and how it acts like a magnetic field. We will then understand how we can leverage this field with a compass needle to enable navigation. Finally, we will discuss how the Earth's core, composed of iron and nickel, generates this magnetic field through the movement of molten materials. So far, you have familiarized yourself with the fundamental characteristics of magnets and the concept of magnetic field lines. You understand how magnetic fields are represented and how they exhibit force on other magnetic materials. Building on this foundation, we can now delve deeper into the interaction between the Earth's magnetic field and a compass. This lesson will enhance our broader understanding of how magnetic fields operate on a planetary scale and their practical implications in navigation. Let's get started.
So, what is a magnetic compass? Jetzt so etwas. Halt.
A magnetic compass consists of a small, lightweight bar magnet called the compass needle, which is mounted on a pivot. This pivot allows the needle to rotate freely in response to magnetic forces. When we think about how a compass works, it's essential to understand that the compass needle behaves like a miniature magnet. Each magnet has two poles, a north pole and a south pole. In a compass, one end of the needle is usually painted red to indicate the north-seeking pole, while the other end represents the south-seeking pole. The Earth itself can be thought of as a giant magnet. It has a magnetic field that extends from the magnetic north pole to the magnetic south pole. This field is not only crucial for compasses, but also has broader implications for life on Earth. It's important to note that there is a difference between geographic poles and magnetic poles. The geographic North Pole is located in the Arctic Ocean, but it corresponds to the magnetic South Pole. Conversely, the geographic South Pole in Antarctica is near the magnetic North Pole. This occurs because opposite poles attract. Thus, the North Pole of a compass needle is drawn toward the magnetic South Pole of the Earth. When you hold a magnetic compass level, the needle, which is a small bar magnet, reacts to the Earth's magnetic field. One end of the needle is marked as the north-seeking pole, often painted red, while the other end is the south-seeking pole. Due to the Earth's magnetic field, the north-seeking pole of the needle aligns with it and points towards the Earth's magnetic south, which we refer to as the geographic North Pole. This alignment happens because opposite magnetic poles attract each other. Therefore, the north pole of the compass needle is naturally drawn towards the magnetic south, geographic north. Conversely, the south pole of the needle is compelled towards the Earth's magnetic north, which is located near the geographic South Pole in Antarctica. This predictable behavior allows navigators to determine directions accurately just by observing the compass needle. The consistent behavior of a magnetic compass reveals much about the Earth's magnetic properties. No matter where you are on Earth, a compass needle always points towards the magnetic north. This global alignment suggests that there is a persistent planet-wide magnetic field influencing the compass needle. The most plausible explanation for this magnetic field is that the Earth itself generates it. Scientists believe that the Earth's core, composed mainly of iron and nickel, is responsible. These metals are magnetic, and the core consists of two parts, a solid inner core and a liquid outer core. The movement of molten iron and nickel in the liquid outer core creates electric currents. These electric currents generate a magnetic field, which extends beyond the core and envelops the entire Earth. This hypothesis would explain the observed phenomena. In summary, the behavior and function of a magnetic compass not only enable navigation, but also offer significant insights into the magnetic nature of our planet. By observing how compass needles align consistently with Earth's magnetic field, we gather evidence that Earth's core must be magnetic. The dynamic movements in the core generate electric currents, which in turn produce the magnetic field that surrounds us. This understanding bridges the gap between simple navigational tools and complex planetary science, showing how fundamental principles of magnetism apply on a grand scale. Watch the rest of the GCSE physics course at Sophos Education,